Okay, hi. I think this looks a little spooky with me in the dark with the light behind me, but we're going to try screencastify on stoichiometry. So I'm going to just see if I can present, and here we go. Stoichiometry is the process of using a balanced reaction to help you solve problems and make predictions about how much of something you can use up or make. So here it is. This goes with a note sheet that I'll be handing you in class and linking to its learning that I would like for you to do for homework due Wednesday when you come to class. And I think this will be a really good chance for you to practice taking notes and using a PowerPoint, Screencastify, and then when we meet, we'll be solving problems together and doing labs. But meanwhile, this will be a good way for you to get used to doing a lesson when you're not in class. So this is homework. Please do it. Here we go. So stoichiometry is just using a balanced reaction as a recipe where all the units in the recipe are in moles. So if you have a given balanced reaction like XA plus YB yields ZC, where A is one substance and B is another substance, and C is the product, and X is the number of A's, and Y is the number of B's, and Z is the number of C's. So you're used to seeing a lot of balanced reactions. We've done those now for weeks. So this is just an example of a balanced reaction with no numbers or actual elements in it, so you can kind of get the idea of the formula. If you had, say, 100 moles of A and you want to know how much you could make of C, here's how you would set it up. You would say 100 moles of A is my given. I would do times in a line, and to get from moles of A to moles of C, I want to put moles of A on the bottom, and so that moles of A will cancel. And from the balanced reaction, you can see that X of A yields Z of C, and so that's where I'm getting this ratio here, where Z moles of C come from X moles of A. See how I'm using the balanced reaction to show moles of X moles of A plus Y moles of B become Z moles of C. Okay, so that's the first one, and that can go in your note sheet. You'll see where that goes. This is the thing that you fill in on the note sheet. All right, here's another example using that same given balanced reaction. If you're given 3 moles of B, you can find out how many moles of A react with it. Here's 3 moles of B times in a line. X moles of A is my answer that I'm looking for. Y moles of B is what I'm trying to get rid of. So that will cross out and cancel, and I'll get 3 moles or 3 times X, because X is on the top, divided by Y, which is on the bottom. And that will give me moles of A, because moles of B is going to cancel out. Okay, something you might be more familiar with is the making of s'mores. So a s'more is 2 graham crackers. I've abbreviated them GC, so it looks like an element, plus 1 marshmallow plus 3 chocolate pieces CPs. And if you put those all together, you make 1 s'more. But technically, that s'more has a formula of GC2 CP3. So here's how I would set it up if I were to do this as a stoichiometry problem to figure out how many s'mores I could make with 25 marshmallows. Now, everybody knows that for every s'more, you use one marshmallow to make it. And that's what this balanced reaction says. 1 marshmallow makes 1 s'more. Here's how I would set it up in my stoichiometry unit factoring if I want to be real fancy. Here's 25 marshmallows. That was my given. Times in a line. The balanced reaction says for every 1 s'more, the GC2MmCP3, I'm going to use up 1 mm. I use up the 1 mm by putting them on the bottom so that they'll cancel, and I get 25 s'mores will be made. The answer is a little bit harder when you're dealing with something that's not a one-to-one relationship. So let's look at if we had 14 chocolate pieces, how many s'mores could we make? Well, I start with my given, 14 chocolate pieces, times in a line, 1 graham cracker, 1 GC2 MMCP3 or a s'more, divided by 3 CPs. That again comes 3 CPs. This is what I'm getting rid of. And 1 s'more is what I want to answer. And I would be able to make 3.7 s'mores with 14 chocolate pieces. And likewise, if I had 4 million graham crackers, I would multiply by 1 and divide by 2 graham crackers to get, oh, sorry, that should say GC on the bottom, 2 GC. I'll have to correct that in a minute. And in fact, let me just correct that now. I will do it as we're speaking, maybe. Oh, it won't let me because I copied and pasted it from something else. Oh, that's really unfortunate. That should say GC. You'll just have to bear with me. Okay. The GCs will cancel and I will get 2 million s'mores. Okay? All right. Next, we're going to do a guided example where we're actually using a real balanced reaction and not a s'more equation. So we have 3.4 moles of aluminum, and it's produced in a decomposition reaction of aluminum chloride, and it wants to know how many moles of chlorine gas is also produced. So here's my reaction. 2AlCl3 yields 2Al plus Cl2. Here's the aluminum. Here's the chlorine. And for every 2 aluminums, I make 3 chlorines. So the ratio will be 2 to 3, or 2 moles of aluminum is produced with 3 moles of chlorine. I don't start with 2 moles of aluminum, though. I start with 3.4, so I write that down as my given. 3.4 moles of aluminum times 3 Cl2s over 2 moles of aluminum. Moles of aluminum will cancel, and I'll take 3.4 times 3 divided by 2 and get 5.1 moles Cl2. All right, let's do another one. In this one, I have propane, C3H8, and I have 0.543 moles of that propane. It's going to combust or burn. It's a fuel. It's the kind of gas that comes with your gas grill that you have outside and cook from in the summertime. I wish we were still using gas grills. It's a little cold for them now. Anyway, how many moles of water will be produced if 0.543 moles of propane is burned? So this is the reaction. I went ahead and wrote it out, came up with my products, 3CO2 plus 4H2O, and balanced to get 5 moles of oxygen, react with it, and that will be 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of CO2 plus 4 moles of water. The mole ratio I need is the one that the question asks for. It compares propane, which is here in the reaction, with water, which is a product in the reaction. The reaction says that for every 1 mole of propane, I'll produce 4 moles of water. So I set it up that way with 0.543 as given, moles of propane, times 4 moles of H2O over 1 mole of propane, and I take 0.543 times 4 divided by 1 and get 2.17 moles of water. All right, that's pretty awesome. Let's try a couple more. If I have 7.8 moles of aluminum hydroxide and they completely react with H2S, how many moles of aluminum sulfide will be produced? So I went ahead and wrote out the double replacement reaction of aluminum hydroxide plus H2S, and I found that the Al combines with the S to make aluminum sulfide, and the H combines with the OH to make water, or HOH, H2O that is. And I see that I have 2 moles of aluminum hydroxide for every 1 mole of aluminum sulfide that is produced. So I wrote that down as the reaction ratio of 2 moles of aluminum hydroxide yield 1 mole of aluminum sulfide. And I started with what I was given, 7.8 moles of aluminum hydroxide. That should be a little 3, not a big one, times 1 mole of aluminum sulfide over 2 moles of aluminum hydroxide, and you make 3.9 moles of aluminum sulfide. All right, so that gives you a really good idea, hopefully, with 3 examples where we had a reaction, we had a starting number of moles, we used the reaction to convert the moles of one thing to the moles of another. That's what we did in each of the reactions. If you look back one more time, we had moles of one thing, we were going to moles of another. In this one, we had moles of this thing, we're going to moles of that thing. Notice it can be anywhere in the reaction. It doesn't have to be reactants and products. It can be products and products. It can be reactants and reactants. As long as the balanced reaction is done for you, or you can do it, you can use the mole ratios in that reaction. Okay, so here's the only thing we have left to learn, and that is that a balanced reaction is a mole recipe, as we've been using, but chemists can't measure moles, they measure grams. So we know how to change grams to moles, and we're going to need to use that skill to make predictions about the amounts of the substances we'll be using and the amounts of the substances we will be producing. We've already had some practice with that with the zinc or the magnesium reaction to produce magnesium chloride, and we're going to be doing that in class tomorrow, Monday, with a hydrate. So you'll have had lots of practice with actually doing gram predictions and changing those to moles to make a calculation. So here's an example of that. I have 77.5 grams of hexane, C6H14, in the following combustion reaction. Notice we produce some CO2 and water, but we really don't care about that in this one. We just want to know how much oxygen we use up. Which, by the way, for every 2 moles of hexane, we use up 19 moles of oxygen. That's a lot of oxygen that's taken out of the air by burning these fossil fuels. The question is how many grams of oxygen gas will be used up. Notice we know that 2 moles of hexane will react with 19 moles of oxygen, but we don't have moles of hexane. So let's find moles of hexane. That's what we're going to do first. 77.5 grams of hexane times 1 mole over the molar mass of hexane will give me the number of moles of hexane as 0.901 moles. Then I can use that reaction ratio that I said was so interesting. 0.901 moles of hexane times 19 moles of oxygen over 2 moles of hexane gives me that I will be using up 8.56 moles of oxygen. Notice that should be 19 to 2 in the ratio of what we started with hexane. And then finally, the question asked us to find the grams of oxygen that was used up. So I changed the moles of oxygen to grams of oxygen. And as you hopefully know by now, to do that calculation, we need the molar mass of oxygen. So that is 32 grams per mole. I canceled out moles of oxygen and got grams of oxygen as my final answer. So 273 grams of oxygen is used up every time we burn 77.5 grams of hexane. Okay, my final reaction of the night. Given a half teaspoon or 2.5 grams of baking soda in a cookie recipe, that is the formula NaHCO3 baking soda, how many grams of carbon dioxide will be produced to help the cookies rise? So I have my balanced reaction here. This is my baking soda. and 2 moles of it produce 1 mole of CO2. So here's my reaction ratio I'm going to be using. Here it is in the calculation. But before we can use it, we have to convert the grams of baking soda to moles of baking soda. So I found the molar mass of NaHCO3 to be 84 grams. I divide by that. 2.5 divided by 84 times 1 equals 0.0298 moles of baking soda. I then take 0.0298 times 1 over 2 to get the NaHCO3 to cancel out and get me my moles of CO2 I'm interested in. And that answer is 0.0149 moles of CO2. And finally, I use my molar mass of CO2 to answer the question, how many grams of CO2 will be produced to help the cookies rise? 0.66 grams of carbon dioxide. Okay, so notice that's this 3-step problem. Change grams to moles, use the molar mass, or use the mole ratio from the balanced equation, change moles to grams because that was asked for. As compared to the first 3 examples where we were given moles and all we had to do was use the ratio. Okay, so those extra 2 steps are if we are given grams instead. All right, hopefully that is enough for you to fill out your note sheet and come to class well prepared for our for stoichiometry on Wednesday. We'll be doing lots of fun problems, and I might even burn up a gummy bear so that we can practice our stoichiometry in the lab as well. I'll see you then. Bye.